Okay, so we are dealing with continuity, which that's a word you've never dealt with before. Are you taking yearbook pictures? Are you taking yearbook pictures?
Oh, yeah.
You only have a second block, don't you? Does she have people first block or fifth block? Do you know?
I don't know.
Okay, I'll talk to her. I'll see her at lunch, but we're doing something tomorrow in class that might be more exciting than like sitting here, but I'll let her know. Thanks. Okay, so let's go ahead and look at continuity. This is a new word. You probably aren't really familiar with it. As you see continuity, we're thinking, what word do I see in here? Continuous. So as I'm thinking, think continuity is like continuous. That's basically what we're looking at. So as I think about the graph of this, we're thinking about basically what we're describing is we're describing functions or graphs that are continuous. So as I kind of just think about it, you can just kind of make some pictures here. What would be a type of graph that wouldn't have continuity or that wouldn't be continuous? Do I? Yeah, so like if I had something like this, so if I had something like this, we'll say a piecewise. So if I have a jump like this, so like this would be considered kind of a piecewise function. So if I have a piecewise function, obviously this isn't going to have continuity over all domain, over all reals. Because as I go from left to right, there's going to be a break, so it's not going to be continuous over all reals. Now, we could be a little more specific and say, is this function continuous on the domain negative infinity to 0? Yes. So you can be kind of specific as a specific domain when you're talking continuity, or if you're talking all reals continuity. I'm trying to think, what types of functions do I know are kind of where always have continuity? Think about functions we've talked about. So what functions do I know will be continuous everywhere? Parabola, so any quadratics, basically any polynomial will be continuous everywhere. Will always have continuity. So any quadratic, x squared, blah, 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 parabola, any linear one, y equals 2x plus 5. So any lines aren't going to have any breaks, so they'll be continuous. What other functions? Maybe not in general, but what other functions do I know never have breaks in them? Trig, a little more specific. Sine, cosine. Tangents on the other ones, we have those asymptotes, so those aren't going to be continuous everywhere. But sine and cosine go on forever, so those would be continuous everywhere. So basically, as I look at continuity, I'm talking about, is it continuous everywhere? Do I see any breaks? Do I see any asymptotes? That's kind of how we talk about continuity. So what we're going to look at today is we're going to kind of put more, I guess, mathy words with the definition of continuity. Like I said on Friday, I want you guys to get used to, at least, even if it's still confusing to you, I want you to be able to get used to at least seeing definitions written out in math. So at least if you take it in college, it's not going to be completely foreign to you. So here is the definition of continuity, besides just saying there's no breaks and it's continuous everywhere. A function f is continuous, and I'm just going to abbreviate it, is continuous at C when, and these are kind of the three components. Now, this is continuity at a point. So this is, the first one is at a specific point. And we'll kind of talk about the difference. It's not really a big difference, but the first thing is how we tell whether something is continuous at a specific point. Now, as we go through this should kind of make sense with what we already kind of talked about, continuity. So the first part is, part A, f of c is defined. Now let's kind of think about what we know here. F of c is defined. So what does that mean? C is just a point, or C is just some x value basically. What does that mean when I say f of c is defined? with what we already kind of know about functions and graphs and stuff. Now we're thinking continuity, so that kind of there's no break on this. So if I say f of c is defined, what's that basically mean? If c is an x value, if it's defined at some specific c or x value, what does that mean? There has to be what value that goes with it? A y value. So basically, if it's defined, it has to have a y value that goes with it. So what type of point can it not have at that x value? How do I represent something? How do I represent on a graph it not being defined at c or at an x value? Open circle. So if I think about this, this is saying that if I have some c value on my graph, if some x value is c, it has to be defined at that c value, which basically means that I have to be able to get a y value. It has to have some y value that goes with that c value. So I'm not going to have an open circle, which makes sense with what we just talked about with continuity. Continuity cannot have any breaks. So if it wasn't defined at c, I would have an open circle, which means it wouldn't be continuous because I would have a break in the function. Okay? So that's the first part. Second part is the limit as x goes to c of f of x exists. So let's think about that. That's kind of bringing in what we did Thursday. The limit as x approaches that value, remember we can go back up in here, look at the graph. C is just some x value. So the limit as x approaches c of the function has to exist. So if I think about what we talked about Thursday, for the limit to exist, what do I know has to happen for a limit to exist? So the limit, remember, limit means from the left and the right. So for that limit to exist, what does that mean about when I approach from the left and when I approach from the right? Has to be approaching the same thing. Why does that make sense with continuity? Because if the limit didn't exist, I could be approaching this way from the left, and I could be approaching, I don't know, somewhere up here on the right. Well, obviously, would that be continuous? No. So that's what I mean when the limit, no, that looks like crap, but that's okay. The limit from the left and the right has to exist, which means from the left and the right has to be approaching the same number. So I keep that nice kind of continuous function. Otherwise, we would have a break like this one. We did this in the notes Thursday. Obviously, this graph, the limit from the left and right didn't equal the same thing, so it didn't exist. Obviously, this graph is not going to be continuous because I have a break. Does that kind of make sense? The third thing that has to exist for continuity is the limit as x approaches c of f of x has to be f of c. I'll kind of explain that. So write that down, let me kind of explain that. What that means, the limit as x approaches c of f of x has to equal f of c. So what that means is that it has to be approaching the same thing that it is equal to. Otherwise, we're going to have a case like this. Like we might have an open circle here and a filled-in circle. So the limit is approaching the same thing. So B is accurate. Left and right, it's approaching the same thing. But they have to be the same, because if not, we might have a filled-in circle down here, an open circle here, and it's not going to be continuous. So they have to be equal to the same number so that I don't have, maybe it's C is defined down here and it's an open circle up here or whatever. Like this example. What is it? Like something like this. These two. Like if I had something like this is what we did Thursday. The limit from the left and the right approach the same thing, and it exists at f of c. At some c value, it exists because there's a y value. But if they're not the same thing, we're still going to have a break like this, and it's not going to be continuous. Does that kind of make sense with math wordy stuff and graph? Okay. It always made more sense if I could kind of look at it in a graph. Now, continuity on an interval, which just means between two x values. So on an interval, all you need for that is it has to be continuous at every point on the interval. So not as complicated, just as I'm talking about continuity over an interval, like I kind of looked at with the graph I drew above it. It has to be continuous on every point. I can't have any breaks, I can't have any asymptotes, I can't have any open circles. Okay, any questions so far on continuity? Okay, let's go ahead and look at example 1. I want to discuss the continuity of a function. So I want to look at this function, and I want to think about the continuity. There you go. You need it still, Antonio? There you go. Sorry. Yell at me if I go too fast. So basically, as I'm looking at continuity, I'm looking for, if I have asymptotes, I'm looking for any open circles. Those are kind of the two big things where I'm going to have, where it's going to mess up my continuity. Are we good?
Yeah.
Okay. So let's look at example 1. I want to discuss the continuity of this function. So as I look at example 1, this is a rational function. It is a fraction. So just by thinking about this, if I'm thinking about the graph of this, I'm thinking I'm probably going to have what? I see the x squared, so I'm kind of thinking maybe a parabola, but I see it's rational. What else do I have to be worried about? Yeah, I'm going to have breaks, but kind of more specifically, what am I going to have in this? If I try to graph this, I don't really have to worry about graphing this, but does anyone wants to know what I'm going to have in this graph? Okay, so if I factor this bottom part, x minus 2, x plus 2, I know that x cannot be what? 2 or negative 2. So what does that mean about my graph? So if I would graph this on Desmos, if you just kind of think about the graph, if I know x cannot be 2 or negative 2, how do I represent values that x cannot be when I graph it? Asymptotes. So these are going to be where my asymptotes are, at negative 2 and 2. So if I think about the continuity of this, you don't have to graph this, but just kind of, if you can visually think about it, I'm going to have asymptotes at negative 2 and 2, because these are going to be values that it cannot exist at. So if I think about the continuity of this is going to be continuous everywhere. Continuous everywhere except where? 2 and negative 2. X equals plus or minus 2. So like I said, continuity, we're worried about asymptotes, we're worried about open circles, holes in the graph. So basically this is going to be continuous everywhere except at x equals plus or minus 2, because that's where my denominator is 0, which is where I'm going to have my asymptotes at. Okay, any questions from that? Okay, let's go ahead and look at example 2 real quick. I want to find the limit, so I'm going back to limits. So if I want to find the limit of each one-sided limit, now this is a little different. These are one-sided limits. So unlike the ones we did last week, where they had to be, the limit had to come from the left and the right, and they had to be the same thing. As I look at this, you will notice the limit as x approaches 4, it has a little plus, and it's like to the right of it. That means that I'm approaching from the right. So as I look at this, now this isn't an accurate graph, but if I just had some graph like this, I don't know, whatever this is. Okay, if I had some graph like this, and let's say this is 4 right here. This is a crappy graph because it's, there you go. Okay, so if I have some graph and I want the limit as x approaches 4, that little plus in the upper right corner means I am approaching from the right. So if I'm thinking about the graph, I would just be looking about the limit as I come from the right. What is my y value approaching as I come from the right? So this little plus means I'm approaching from the right. I do not care about approaching from the left. I only care about approaching from the right. But you treat it the exact same way we would evaluate it we did on Friday. So as I look at this, anytime I try to do a limit, I always try to do what first? Plug in a 4. It's done the same way. Now if you look at a graph, it would be a little different, but doing it by plugging it in is done the same way. If I try to plug in 4, I'm obviously going to get a what? 0 in the denominator, so the next option is try to do what? Factor, rewrite it. In this case, we can factor the bottom, x plus 4, x minus 4. Now we're close. We can't quite cancel anything out. Anybody see what we can do? Do what? Yeah, I can factor a negative on the bottom, or I'm just going to factor out a negative 1 on the top, which will make it a little easier. You will get the same answer, but I'm going to factor a negative 1 on the top. So if I factor out a negative 1 on the top, that'll give me a negative 4 plus x. It's the exact same thing. If I would distribute a negative 1 through, I'd get the same thing. I'm just rewriting it so I can work with it. So now, what's going to cancel? X minus 4s. So I'm left with a negative 1 over x plus 4. So now, as I try to evaluate the limit, like I said, even though it's from the right, we evaluate it the same way. Plug in the 4, negative 1/8. So now we're just working with one side limit, which is basically the same idea. Now the graph, it would be a little different, but evaluating it's the same thing. Any questions on that? Okay, let's look at B. If I look at this, now this is a negative in the top right corner, so this is approaching from the left. So if I would look at a graph of this, I would only be worried about the limit approaching from the left. Obviously, if I try to plug in 4, it's going to give me a 0 in the denominator. Any thoughts on how I could do this? Yep, square root of x plus 2. Let's try to rationalize this. So kind of like we did Friday, anytime I see a square root, I'm thinking, well, let's try to rationalize it, see if it gets me anywhere. Just like if you see compound fractions, let's try to get common denominators, see if that gets me anywhere. So as I look at this one, we're going to have basically you're foiling on the top. So I'm going to end up with what on top? Yep, square root of x times square root of x is x. The middle two terms will cancel. Negative 2 times 2 is negative 4. So x minus 4. Like I said, in the denominators, usually don't multiply them through because we're looking for things that cancel. And this worked out pretty nicely. Right off the bat, I notice my x minus 4's cancel. So I just have the limit as x goes to 4 from the left over 1 over square root of x plus 2. We treat it the same way when I'm plugging it in. So that is just 1 over square root of 4 plus 2. So 1 over 4. Okay. Any questions so far? Okay. Example 3, the limit of the greatest integer function. Now, I don't think, did you do greatest integer, and does this look familiar from pre-calc? I don't know if you did or not. Okay, but first thing I can see, so that would be confusing to me right off the bat. The symbol that I don't really know what it means, that would be confusing to me. But I notice I have the limit as x approaches from the 2 from the right. So that's something to think about. I also notice I have 2x minus the greatest integer of function, basically. So I don't really know where to go from this, but what can I do with a limit? If I'm subtracting two things, I can just do what with it? We don't necessarily do it very much, but we did it like Friday. I just showed you 1 or 2 examples like it. I remember. We technically can just split it up. So even though I never really do this with polynomials just because it's kind of redundant, you can technically split it up like this. Okay? So if I split it up like this makes it at least a little more doable. Because as I look at my part on the left, I can just do what for the part on the left? Plug in a 2, so that's just going to be 4. We're good with that. So at least it makes it a little more doable. We still know nothing about the greatest integer function, but at least it makes it a little more doable. Now, as I look at the greatest integer function, this is what it looks like. This is kind of the definition. You don't work with it very often. We're not going to work with it a ton, but just so you kind of have seen it, this is what it looks like before. So this is what it looks like. Basically what it is it takes, let me see if it's always hard for me to explain. So it looks something like this. Let's get a picture drawn in. It's also called a step function, which that makes a little more sense then. So basically that's what a greatest integer function means. So basically what that says, it's taking your decimals and rounding them. How do I want to word this? It's rounding your decimals to the greatest integer. So if I do, it's always confusing how I want to word it. I'm not going to try to explain it because it's going to make it more confusing. But this is what it looks like. This would be the parent function of the greatest integer function. Okay? So as I look at this, now we're just going to look at the graph. I want to know what is the limit as x approaches 2 from the right. So here's my greatest integer function, the graph. As I approach 2 from the right, what is my y value approaching? So as I approach 1, 2 from the right, my y value is approaching from the right because of the plus. So as I look at when x is 2 and I'm approaching from the right, my y value is 2. So this is just minus 2. So I'm approaching when x is 2 from the right, so the y value is 2. So it's just 2. So that's just finding the limit from the graph. Because, like I said, we did it Thursday, but then Friday we kind of found easier ways to do it. But with greatest integer, there's not really any way to do it. We don't really know how to work with it, so we just have to look at the graph. So that is just 2. Okay. Any questions on that? Okay. Let's go ahead and look at a couple things. Let's skip down to the definition of continuity on a closed interval. I want to make sure we can get through everything, so I'm kind of trying to pick and choose what is important. So definition of continuity on a closed interval. So once again, it's a definition, so let's just write it down. Like I said, I know this is going to be confusing. I know this is going to be some big words that don't make sense. Let's write it down and let me kind of explain it. I want you to at least be able to kind of be familiar with them. A function f is continuous on a closed interval and we're using brackets because it's a closed interval, which means it can be equal to the endpoints a and b. So let me great, that made it worse. This is stressful. Right. Nailed that. Anytime. It's like that one thing in the eye doctor. Is it better at A or 2? I don't know. It looks the same. And then I feel bad. read the last line, and then I can like read the second line down, and then they're judging me. Anyway, okay. So a function f is continuous on a closed interval ab, and we're using square brackets because closed means that the left and the right it can be equal to. So function f is continuous on a closed interval ab when f is continuous on the open interval AB, which it's open, so now we just have parentheses. So when f is continuous on the open interval AB, which is basically saying, okay, it's continuous in the middle. So if I think about my function, and here's A and here's B, basically I want to show it's continuous on that closed interval. What I'm saying right now is, okay, when f is continuous on the open interval, so it's continuous in between A and B, but I don't know about the endpoints, because it's only continuous on the open interval, so it's only continuous between A and B. And the limit as x approaches A from the right of f of x equals f of A, and the limit as x approaches b from the left of f of x equals f of b. So write that down and let's think about this. Because hopefully as I explain it, it'll make more sense. Trust me, if this is confusing, that is just fine. It took me 2 years of Calc in high school and 3 years of Calc in college, and then teaching it to actually be like, oh, this makes sense. So I just want you to be at least, you're not going to have to memorize this or write this down. I want you to at least be able to look at it and try to understand it. So as I look at this, we have the limit as x approaches A from the left or from the right. So what this is saying, as x approaches A from the right, so as I look at this picture, I'm approaching A from the right here, of f of x equals f of a. So what does that mean? So if I just look at this, it has to equal, if I say f of a, that's basically the what? If I say a is just an x value. So if I do f of a, that is the y value at a on the function. So what that's saying is the limit from the right has to be equal to what I would have it, the y value, if I would plug a into the function. It basically means it has to be that filled in circle. So that limit from the right has to be equal to what my y value, what my point would be if I plugged in a here. Same thing with b. As I approach b from the left, what that's saying is that has to be equal to the y value, or the point, if I plug b into the function. That's what it's meaning, okay? Like I said, don't worry 100% about this definition making complete sense. I just want you to be able to get used to seeing how things are written. Okay, let's look at example 4. I want to discuss the continuity of each function on the given closed interval. So as I look at example 4, this is a closed interval because I have brackets. So closed interval means I include the endpoints, left and right. So as I look at this, we're going to use the definition of continuity on a closed interval we just wrote the definition for. So what that's saying is, first of all, first thing we need to check, as I look at my definition, a function f is continuous on the closed interval ab when f is continuous on the open interval ab. That's the first thing we want to check. Is my function continuous on an open interval -3, 3? So is it continuous in between the endpoints is what we're looking at. So let's go back to this example and say the first thing we need to check for is continuous on the open interval negative 3, 3. That's the first thing that has to be true. Is this continuous on the open interval negative 3, 3? That's the first part of the definition we have to show. Now we can kind of think about this with what we talked about domain and range. As I look at this, this is obviously a square root function. So if I think about, okay, what values, I cannot take the square root of what? Negative. So I want to basically think about, okay, will I get back a value if I plug in values from negative 3 to 3, not including negative 3 and 3, will I be able to take, will it exist, is what we're basically looking for. So if I plug in negative 2 or negative 1 or 0, 1 or 2, will I always be able to take the square root? Yes, so I know it will exist, so it will be continuous. So it is continuous on the open interval negative 3, 3. You can just kind of think about it. Think about same idea as domain and range. Will this function exist between negative 3 and 3? Yes. The second thing, the second part of the definition is I need to show the limit as x approaches. The definition says a from the right. In this case, it's going to be as x approaches, instead of a from the right, this is going to be, so here's this. The limit as x approaches a from the right, which in this case, instead of a, is going to be, yep, a, b is my interval. So this is going to be negative 3 from the right. So as x approaches negative 3 from the right on my function, I want to show that, here's my function, 3 minus the square root of 9 minus t squared. That limit has to be equal to what? Look at the definition. The limit as x approaches a from the right has to be equal to what? F of a. So in this case, it has to be equal to f of negative 3. So what I'm saying is I'm saying that if I evaluate the limit from negative 3 from the right, that has to be the same as just plugging in negative 3 into the function, which, if you kind of think about it, is basically what we're doing anyway. So if I plug in a negative 3 here, I'm going to get back the square root of what? 0, so I'm just going to end up with 3. And basically, if I plug in a negative 3, it's kind of redundant. It's basically what we're doing anyway. I'm also going to get back a 3. So we are good with that. Same thing. Limit as x approaches. Now the definition says b from the left. In this case, it's going to be 3 from the left of the function. Has to be equal to f of b, or f of 3. So if I plug in, if I find the limit of 3 from the left, I plug in a 3. Same sort of idea. 3 squared is 9. Square root of 9 minus 9 is 0. So it's just going to be 3 equals, if I plug in a 3, I'm basically doing the same thing. So we're good. So what that means is that it is continuous on negative 3, 3. So what we're showing by doing that is that it is continuous on that closed interval, negative 3 to 3. Okay. Any questions on that so far? Okay. Let's look at continuity of a composite function. Let me just write this down real quick. If, I don't leave you much space, if G is continuous at C, so G is just a function, so we're talking composite, so we usually deal with F and G. If G is continuous at C, and f is continuous at g of c, then the composite function f of g of c is continuous at c. Okay, like I said, don't get too worried about doesn't make sense. Blah, blah, blah. I'm going to kind of break it down as we look at some composite functions. But that's just kind of how we tell whether a composite function or what continuity a composite function has. Okay, so let's look at example 7. So as I look at example 7, we kind of are doing the same thing. So you don't necessarily have to worry about like the composite part of it and try to figure out what parts are continuous. Just kind of look at it and do like we did earlier. So as I look at this function, as I look at A, I look at this, I have a rational function, 1 over x squared plus 1, and I want to kind of think about, okay, what parts are, find the x values, if any, at which f is not continuous. And then which of the discontinuities are removable. When I say removable, I'm saying an open circle. Okay? So removable would be like an open circle, not an asymptote. An asymptote would not be considered removable. Removable would be like a hole or an open circle. So as I look at A, am I going to have, easiest way to think about the same way we did with domain and range. Am I going to have any asymptotes as part of this graph? So is there any values of x that I cannot plug in for this function? No. Even though it's a rational function, there's going to be no asymptotes on this. There's no values of x that I cannot plug in. I can plug in 0, I can plug in -1, I can plug in 1. There's no way I can get back a negative or a 0 in the denominator because I cannot square anything and get back a -1. So this is continuous on all reals. So we're kind of doing the same thing we did earlier. We're looking for asymptotes, kind of like we did with the domain and range. Same thing with B. B, it's a trig function. Anytime, if I'm dealing with sine or cosine, it is almost always continuous everywhere. So since this is cosine, this is also continuous on all reals. There's not going to be any breaks to this. We're going to have that nice curve the entire time. Now, as I look at part C, we kind of talked about this earlier. This is going to be what type of function? Piecewise. So in the back of my mind, am I thinking this is going to be continuous everywhere? No, because like the one we did right when we started talking about continuity, I'm thinking we're going to have a break somewhere. Okay? So as I kind of look at this, you don't have to necessarily worry about the graph. You can kind of think about this and think about, okay, if I will think about the graph, what x value am I thinking I'm going to have be discontinuous at? What x value is going to kind of screw up my continuity? 2. So we're thinking 2 is kind of the x value where we're thinking, okay, let's check that and see what my continuity looks like at 2. So what we want to check is we want to check like the very beginning. We want to check what about my continuity at a point. So we have 3 things we need to check for. First thing we need to check for is, we're going all the way back to the, you don't have to flip back. I want to check the continuity at a point. This is what we're doing. These 3 steps to see, is this function continuous at the point x equals 2? So we're checking continuity at a point. So first thing we need to show is f of c is defined. So first thing is f of 2 defined. So basically, does f of 2 exist? So if I say f of 2, what is f of 2? If I would evaluate f of 2, does it exist? Is there a y value that goes with f of 2? How would I evaluate this? Plug in 2 to which one, the top or bottom? Top. Less than or equal to 2. When x is less than or equal to 2, so I plug in 2. So negative 2 times 2, negative 4. So does this exist at f of 2? Yes. When I say does it, or defined is the word. Is it defined? It is defined because there is a y value that goes with it. Second part I need to show is I need to show the limit as x approaches 2 of f of x exists. That's the second part. Does this exist? Does the limit as x approaches 2 exist? So as I think about this, you can think about a graph if you want to. If you want to graph it, you don't have to necessarily. It doesn't have to be a perfect graph. But here's whatever. Negative 2x, this would be 0, up, rise over run. Up to, well, something like that. At 2, I know it's going to be negative 4. This is going to be something like that. Whatever. And I have this parabola that I'm not going to worry too much about, but if x is greater than 2, you can kind of look at it. I'm not going to worry too much about graphing this. Let's just say it's graphed like this. I don't know. It's going to be something like that. Is this, you don't have to draw a perfect graph just to kind of see, is this limit as x approaches 2 going to exist? No, the left and the right are not going to be the same. So no. So it is not going to be continuous at 2. So this is not continuous. So find the x values at which f is not continuous. Not continuous at 2. And that would be a jump when they say, not jump, discontinuous, removable. This is removable. Anytime if I have an open circle, which I would, because I have x is just greater than 2 and not equal to 2, that is removable. Just so you know, I'm not too picky about it, but that's considered removable. Okay, any questions so far? Yes?
On the piecewise, should that ever be continuous? Since
It shouldn't be. Usually they won't be continuous. The only way it would be continuous is if this, like you do a piecewise, which is possible, not very often, like this, and then this picks up right where you left off. So that kind of makes sense. Every once in a while you'll see it, but usually you don't. Any other questions? Okay. Let's go ahead. Intermediate value theorem. This is one we're going to use a lot. So let's write this down and then I'll explain this. So if f is continuous on the closed interval AB, so you don't have to write, you can just write this. So f is continuous on the interval AB and it's closed, so I'm using the brackets with AB. F of A cannot be equal to f of B. And K is any number between f of A and f of B. Then there is at least one number C in the interval AB such that f of C equals K. So write that down and I'll explain that. And hopefully as I explain it, it'll make a little more sense. Okay. So let's go ahead and kind of sketch a picture. I think a picture is helpful. Picture always helps me. So f is continuous on AB. So let's say A, B. Those are that's my interval. So basically, those are my x values. It is continuous. And it's a closed interval. So it should look something like that. And what does it say when it says f of A cannot equal f of B? That basically means what? Remember, f of A is the y value at A and the y value at B. So if the y value at the left and the right endpoint can't be the same, basically I can't have what type of line? Straight horizontal line. Okay. K is any number between f of A and f of B. So K is really talking about a y value. So if this would be f of A, this would be f of B. So K is going to be some number between f of A and f of B. Because f of A, when I say f of A, I'm saying the y value when x is A and the y value when x is B. So I labeled f of A and f of B. K is some number between those. There is one C number in the interval such that f of C equals K. So there is some C number in that interval, so between A and B, where f of C is K. So when I plug C into the function, I get back a K. So the y value when x is C is K. That's what I'm talking about. Which is kind of intuitive, and you're like, okay, that kind of makes sense. That it has to stay in between the y value, so it has to stay in between the x values. But that's the intermediate value theorem. Okay, so let's look at one example with that. You have one example to look at with that. You will see this on the homework, and you'll see this on the study guide and notes. So please let me know if you have questions on that. So example 8. I want to use the intermediate value theorem to explain why the function has a 0 on the given interval. So when I say it's a 0, basically I say the C value is the same as a 0. Because remember, a 0 is just a point on the x-axis, and C had to be between A and B, so it had to be on the x-axis. So we're going to go through that whole process. So the first thing we have to look for is we have to show that f of A cannot equal f of B. So this is the first thing we're looking at. This is part of the intermediate value theorem. F of A cannot equal f of B. If it does, then we have a horizontal line and we can't use the intermediate value theorem. F of A cannot equal f of B. So this isn't really that hard to show. F of A, if I would do f of A, in this case it would be f of 0. We've done this as algebra 1. If I plug in 0, that's going to give me back a 0 minus 2 minus cosine of 0. Cosine of 0. So negative 2 minus 1, that gives me negative 3. So I evaluated f of 0, or f of the left endpoint. Now I want to show f of b, and I want to show they're not equal. So in this case, f of b will be f of pi. So if I plug in pi squared minus 2 minus cosine of pi. Cosine pi. What is cosine pi? Negative 1. So pi squared minus 2 plus 1, because I have a negative out front already. So pi squared minus 1. So I don't really care if I have pi in there. Pi is 3.14. So will 3.14 squared minus 1 ever give me back negative 3? No. So f of A does not equal f of B, so that is the first part. So we're good with that. The second part says that K is any number between f of A and f of B. So we're going to show that f of C equals to 0. This is my K value. So I want to show I want to show that there is a 0, which means that this has to be equal to 0. So I want to show, if I want it to be a 0, my f of C has to be equal to 0. And this k value has to be between f of a and f of b. So is 0 between f of a and f of b, which is pi squared minus 1. So k has to be between those two y values. Is 0 between negative 3 and pi squared minus 1? Yes. So we are good. So that's how we show the intermediate values. So brand new. The actual math isn't super terrible. It's just that definition. It's brand new. You haven't worked with it a whole lot. Okay. So we're good with that. Homework, get the homework out. You don't have a lot of time. Sorry, I'm doing my best to give you time, but some days it's just going to be what it is. Okay, get the homework out. I'm going to take off a couple.